Today's video is made possible by Brilliant.org. Today I'd like to show everyone a really cool counting object known as the Q binomial coefficient, or to jazz it up sometimes it's called the quantum binomial coefficient. And so I've entitled this binomial coefficients, quantum and otherwise, but there's probably more of a clickbait title on YouTube. So we'll start this video by looking at the definition of regular binomial coefficients as well as what they count, before moving on to these Q binomial coefficients, or sometimes Q analogs of binomial coefficients. So let's recall, by definition, N choose K is the number of ways to choose K objects from N objects, where the ordering of those objects that we have chosen does not matter. So a classic example of this would be to take a 2-element subset from a 4-element set. And we might as well call that 4-element set 1, 2, 3, 4. So let's notice we can pretty easily just write down all possible 2-element subsets. We have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. But we can count that up and we see we have 6 total 2-element subsets of our 4-element set, meaning 4 choose 2 is equal to 6. Well, likely if you're watching this video, you know the closed form for a binomial coefficient, and that's this claim right here, which we will sketch 2 proofs of. We're not going to do these super carefully, that's why I say they will be sketches. So N choose K is defined to be N times N minus 1 times N minus 2 all the way down to N minus K plus 1 over K factorial. Let's notice that that numerator is a product of K objects starting at N and then descending by 1 at each step. There's like a more closed form of this that you might recognize, N factorial over K factorial times N minus K factorial, but I like this format better because it generalizes to non-natural numbers up here very easily. Okay, so let's look at our first sketch of this proof. So let's say we want to choose the first element from our N element set. But how many ways can we make that first choice? Well, there are N elements, so there are N possibilities. So we'll just say there are N possibilities for choosing this first element. But after we've chosen that first element, we have how many elements left to choose from? Well, we have N minus 1 to choose from because we've already taken one of them out. So our second choice has only N minus 1 possibilities. And likewise, our third choice will have N minus 2 total possibilities. So I'll just say this parentheses with the line is just bringing down the word possibilities. And then let's go all the way down to our kth choice. And notice that this is the last choice that we will make because our aim is to have a K-element subset, just by our definition over here. So how many choices are there left here? Well, there are exactly N minus K plus 1, because that's how many elements are left in the set. So there are N minus K plus 1 possibilities in this case. But now let's notice that once the set is made, we may have made the same set many, many different ways. Because what if we took our first choice to be like the number 1 and our second choice to be, for instance, the number 7? Well, that's equivalent to taking the first choice to be the number 7 and the second choice to being the number 1. So that means we've duplicated a lot here. And how much have we duplicated? Well, we've duplicated the number of permutations of a K element set. So I'll just put K factorial duplicates. But now by the multiplicative property of counting, we know that our total possibilities, which we're defining to be N choose K, will be the product of all of these possibilities divided by the duplicates. So in other words, we have N times N minus 1 times N minus 2 all the way down to N minus K plus 1 over k factorial. And that establishes this formula. Now let's quickly sketch another proof before we move on to an application. So our second proof considers the binomial 1 plus x to the n power. And so this is why this is called a binomial coefficient. So we can write this as 1 plus x times 1 plus x times 1 plus x, so on and so forth, where we have exactly n copies here. So we're multiplying that to itself n times. But now let's notice that the coefficient of x to the k power in this expansion will be exactly n choose k. And why is that? Well, that's because we have to choose k times to choose x instead of 1 from each of these products to achieve x to the k. But that's exactly the same as choosing a k element subset from an n element set. So that's our binomial coefficient there. But what that tells us is that this expands as the sum as k goes from 0 to n of n choose k times x to the k. And then how do we prove that this n choose k is exactly this product up here? Well, there are a number of ways to do it from here, but they all are built off of this following, like, really simple trick involving this 1 plus x to the n. So let's notice that 1 plus x to the n power is the same thing as 1 plus x to the n minus 1 times 1 plus x. And then you can expand this one that I'm boxing in magenta using this rule and distribute it over this 1 plus x and then finish it up with induction. So this is more of a sketch than the last one for sure, but in fact we'll look at something similar to this when we look at the quantum binomial coefficients. So I think it's okay to be a little bit hand wavy here. Okay, so now let's look at an example of what these binomial coefficients count, maybe a nice geometric example. So here's a classic counting example of binomial coefficients. So let's suppose we're given an m by n grid, and our goal is to count the number of paths from the bottom left of this grid to the top right of this grid, where the only allowed moves are up and right. Which means if we make a turn, we can only make a left turn. That's another way to think of this. So one such path would look as follows. Maybe we could go along this bottom edge for 2 steps, then we could go up this for 2 steps, and then we could do a 1 and a 1, and then across 3, for instance, and then a 1 and a 1 and a 1, and then across 2. So that would be an example of one of these paths. Now, you can play with the small examples for yourself. In fact, I think a 3 by 2 example is a really nice small example to look at. And as you can see, we can easily enumerate through all possible paths in a 3 by 2 grid, and we'll see that there are 10. And now we just need to relate this number 10, the total number of paths, to the numbers 3 and 2 in terms of binomial coefficients. But that's not too hard to do if you play around with it a little bit. And what you'll see is that 5 choose 2 is in fact equal to 10, but 5 is equal to 3 plus 2. So in a 3 by 2 grid, the number of paths is 3 plus 2 choose 2, which is the same as 3 plus 2 choose 3. So this is like symmetric about some sort of flip. And that really maybe sets us up for the following claim, which actually has a very, very simple proof. And that claim is that there are m plus n choose n such paths. And when I say such paths, I mean paths that are following the rules up here. Okay, so how might this proof go? Well, like I said, it's really quick. So the first thing that we note is that the path follows exactly m plus n edges. And since we're only allowed to go right and we're only allowed to go up, we have to go right exactly m edges and up exactly n edges. So let's maybe put that. So m are to the right, and then n are up. So that means at any vertex, we can make the choice to go right or up, but we make m choices to go right, just by design. So that's just like choosing an m element subset from an m plus n element set. So that means the number of paths here is equal to exactly what we want. M plus n, choose m, which, like I pointed out before, is the same thing as m plus n, choose n, by the definition of the binomial coefficient, or by the closed form we had. You can see that as well. Okay, so now that we've looked at this, I want to introduce the notion of a Q binomial coefficient, and we'll see how that relates to this path problem.
Hang on there a second past me. I need to tell everyone about today's sponsor, Brilliant.org. Brilliant is a website, sure, but their approach to learning is the star of the show. Brilliant's visual, hands-on approach can be your key to understanding the concepts behind today's technology, which is crucial to staying ahead. You can explore a variety of topics and skill levels. Brilliant will support you every step of the way. Gradually, you can master whole topics in as little as 15 minutes a day and learn anywhere, anytime on your phone, tablet, or computer. Brilliant makes learning more like a game, with fun features that let you challenge yourself and compete with others. Recently, I've been teaching a Calculus 2 class, and I thought that I'd check out what Brilliant's calculus offerings look like. And was I ever impressed by what they have to offer? Great visuals, intuitive explanations, and they gamify learning. If you'd like to level up your math and STEM skills and experience the joy of learning, go to Brilliant.org and treat yourself to a unique hands-on experience. A 30-day free trial, and the first 200 people will get 20% off their annual subscription. Thanks once again to Brilliant for sponsoring today's video.
So now that we've reviewed normal binomial coefficients, let's look at their Q analogs. So let's say we're given this bracket n sub q is equal to 1 minus q to the n over 1 minus q. Then the binomial coefficient n choose k q is this descending product of these q analogs of natural numbers, in fact. So nq, n minus 1q, all the way down to n minus k plus 1q over kq factorial, but I've just written that as a descending product. In fact, I recently did another video on the quantum factorial, and this is all related to this. But then a pretty simple homework exercise of just moving some things around and canceling out when necessary shows that this simplifies to the following object. We have 1 minus q to the n times 1 minus q to the n minus 1 times 1 minus q to the n minus 2, ending at 1 minus q to the n minus k plus 1 over 1 minus q to the k times 1 minus q to the k minus 1, all the way down to 1 minus q. Okay, then the real question here is, how does this relate to counting? And I think the easiest way to start to look at that is to look at our example that we had of the 3x2 grid. And again, work through all of the paths from the bottom left to the top right. But now, instead of just counting the paths, let's look at the area of the squares under those paths. And that gives us the following chart. And the area can be encoded in the exponent of q. Notice that after all is said and done with this simplification, these will indeed be polynomials. So maybe we would get something like this. So we have 1, just the plain old number 1 times q to the 0. That's the counting of the path with area 0. And then we'll have plus q to the first power. So that's the counting of the path with area 1 plus 2q squared plus 2q cubed. So that's the counting of the paths with area 2 and 3. Finally, plus 2q to the fourth, that's the path with area 4, and then plus q to the fifth plus q to the sixth. And we want this to look pretty similar to what we had when we were just counting the paths up. So let's try to get there. So we can in fact factor this thing, and it's maybe not immediately obvious, but after looking at it for a little bit, it will be kind of pretty clear. It will factor as 1 plus q squared plus q cubed plus q to the 4th times 1 plus q squared. Okay, nice. But now we can turn that into a rational function that looks a little bit nicer. And that rational function will be 1 minus q to the 5th over 1 minus q. So that's what we get from multiplying this first term by 1 minus q over 1 minus q. And then we can multiply the second term by 1 minus q squared over 1 minus q squared. So that'll give us a 1 minus q squared in the denominator. And in the numerator, we'll have 1 minus q to the 4th. But now that looks suspiciously like one of these q binomial coefficients. And in fact, it's the q binomial coefficient, which is 5 choose 2 or 5 choose 3 q. Those are the same, like I pointed out before. And just to really flesh this out in terms of what we had before, this is equal to the quantum binomial coefficient 3 plus 2 choose 2 q. So it seems like when we expand this quantum binomial coefficient, or this q analog of the binomial coefficient, what we're getting for certain coefficients of a power of q are the number of paths with a certain area under that path, if you will. Okay, so now let's prove that. So now for the main result of the video. And that is, if we take this sum as k goes from 0 to m times n of a sub m n k, q to the k, where a m n k is the number of paths in our setup that we've been working with area k, then this is equal to the q binomial coefficient m plus n choose n q. So in fact, this is a generating function for the number of paths of a certain area. That's maybe how you would say that in a combinatorial way. So I've got a picture of a path over here with its area. So notice the area here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 17. So the area there is 17. But there's a bunch of other ways in that grid that you could get an area of 17. Okay, so here we're going to use induction, and we're going to use induction on n. But let's notice that that is equivalent to induction on m, and it's equivalent to induction on m because m and n play symmetric roles here. In fact, working with an m by n grid is the same thing as working with an n by m grid that we were just to like rotate a little bit. So that's really no big deal. Okay, so let's look at our base case. So like I said, since we're working with induction on n, our base case will be n equals 1. I guess we could take the base case of n equals 0, but that's kind of boring. So for the n equals 1 case, our grid looks like this. So we have just essentially m boxes there. So let's point out that we have m boxes. Okay, so how many paths are there from here, this left bottom endpoint or corner, to the here? Well, there will be exactly m plus 1 paths, and we know that from the previous problem. But notice each path has a certain area, and it's the only path with its given area. So for instance, our path like this, say we go along the bottom for a long time and then up and then over, that has an area of 2. Whereas this one that goes straight up here and over has an area of m. And finally, this one that just stays along the bottom and goes up has an area of 0. So the smallest possible area is 0, the largest possible area is m, and we can get every area in between exactly one way. I think that's pretty clear. So our right-hand side, this object over here, which maybe we'll give that thing a name. Let's say the right-hand side is this function g of mn. So it's a function of m and n. And q is not really seen to be a variable. It's seen to be like some sort of parameter. So notice that we have gm1 is equal to 1 plus q squared ending at q to the m. But that's exactly equal to 1 minus q to the m plus 1 over 1 minus q, just by the sum of a finite geometric series, but that is exactly m plus 1 choose 1 q. Okay, nice. So now that we've got the base case taken care of, let's do the induction step. Okay, now for the induction step. Let's recall that I called this right-hand side GMN, just for simplicity. Now, let's suppose that our setup is true for some n bigger than or equal to 1, and then we will consider the n plus 1 case. So that means we've got an m by n plus 1 grid. And the idea here is to break up the paths from this origin part over here to our n plus 1 vertex over here into a couple of different possibilities. So let's maybe label this origin in blue, just so that we've got something to work with, like some nice notation. And then let's label this kind of goal point at the end in green. Okay, and then furthermore, I'm gonna label this point right here in magenta and this point right here in yellow. Okay, good. So we can break down our paths from blue to green into whether they go through this yellow dot or whether they go through this magenta dot. Notice they have to go through one of them. So paths from blue to green, or the number of paths from blue to green, can be split up into the paths from blue to magenta times the number of paths from magenta to green. Well, there's only one of those paths, but we need to keep that into consideration because we're also counting area. Or the paths from blue to yellow, and then the paths from yellow to green. So we have multiplication there to like count all of our possibilities, even though there's only one path in these other ways. Okay, so let's recall that using our notation, the paths from green to blue are counted with the generating function g of mn plus 1. Then the paths from blue to magenta are counted by the generating function g m minus 1 n plus 1, because that's in an m minus 1 n plus 1 grid. And then the path from this magenta to this green, there's only a single path, but notice that single path has an area of n plus 1. That's just by the area of a rectangle. So that means we need to multiply this by q to the n plus 1. And that's because we increase the area of all of the paths to the magenta dot by n plus 1. Okay, so that's that bit. And then we'll have this is plus the paths from blue to yellow, but that's an m by n grid. So that's given by the generating function g of mn. And that's because the path from yellow to green there doesn't give us any extra area. So this gives us this nice recursion on the generating function for these paths. And now we're ready to essentially finish this thing off, but we need a little bit of extra room. So starting with the recursion that we just developed, we can apply the induction hypothesis to these two terms. So obviously we can apply it to this brown overlined term, but we can also apply it to this term just by using the symmetry of the m and n. Okay, so now let's do that. That's gonna give us qn plus 1, and then we'll have m plus n choose, let's see, n plus 1 q. So that's our binomial coefficient there, and then we'll have plus m plus n choose n q. Great. And now we'll expand each of these out using this homework. And so what will that leave us with? We'll have q to the n plus 1, and then this one will be 1 minus q to the m plus n times 1 minus q to the m plus n minus 1, all the way down to 1 minus q to the m, and then this is all occurring over 1 minus q to the n plus 1, all the way down to 1 minus q. Great. So that would be the expansion of this first q binomial coefficient. And for this second q binomial coefficient, we'll have something like 1 minus q to the m plus n, all the way down to 1 minus q to the m plus 1, and then this is all happening over 1 minus q to the n, all the way down to 1 minus q. Great. But now we'll build the denominator in this second term so that we can combine it with the first term. So notice that all it lacks is this 1 minus q to the n plus 1. So let's multiply that in. So maybe I'll sneak it in over here. We have 1 minus q to the n plus 1. That's going to go there. It's also going to go here, 1 minus q to the n plus 1. But now our denominators are the same. So let's also notice that this descending product in the numerator of the first term goes a bit further than it does in the second term. This first term stops at 1 minus q to the m, whereas this one stops short by 1 at 1 minus q to the m plus 1. So I'll underline in this one in purple to show that it is extra. And that's going to be where all of the cancellation comes from. So notice multiplying this q to the n plus 1 onto the number 1 right here, and then onto all of the other terms as well, along with multiplying this q to the n plus 1 onto all of the terms right here will cancel. So in other words, all of these red overlined terms will cancel. And then all of the ones that'll overline in blue will build up. So we'll have this q to the n plus 1 here will combine together with this q to the m here, and then be subtracted from the number 1 here. And that's because what we're left over here, which I have in magenta overline, is the same thing as what I have left over here in this magenta overline. So in the end, we'll have 1 minus q to the m plus n plus 1. So the 1 comes from over here. The m plus n plus 1 comes from that blue overline. And then we'll have 1 minus q to the m plus n, which picks up right here, and then descends all the way down to 1 minus q to the m plus 1. And then in the denominator, we've got this descending product, 1 minus q to the n plus 1, all the way down to 1 minus q. But that's exactly our binomial coefficient, or our q binomial coefficient, and it's exactly the one that we want. This is m plus n plus 1, choose n plus 1 q, which finishes the proof of this claim. So recently I did another video, which I think I mentioned earlier. That should be on the screen right now if you'd like to check it out. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.